Okay, picture this. You're sitting at a desk, no computer, no soldering iron, just a piece of paper and a pencil. And you draw a thick, dark line on that paper. Then you clip a couple of wires to it, you look at a multimeter, and you realize something kind of profound.
Right, you haven't just made a drawing.
Exactly. You've just manufactured an electronic component.
It's a powerful moment, isn't it? It forces you to realize that electronics isn't just about code or symbols on a PDF. It's physical.
It's material science.
It's graphite and chemistry and geometry all in one.
That is exactly what we are unpacking today. We're looking at a curriculum that's designed to take students from, textbook theory and drag them, maybe kicking and screaming, into the messy, real world of getting your hands dirty.
And we should say, right up front, credit where it's due. This whole philosophy, all these experiments we're about to discuss, they come from a list that was very carefully curated by Dr. Dhananjay Godre for the Electronic Design Workshop course at NSUT.
So this isn't just a random list of, internet science hacks. This is a structured university course.
Precisely. And Dr. Godre's mission here seems very specific. It's about breaking the habit of thinking components are perfect little black boxes.
Right, because in a simulation, a resistor is perfect.
It's perfect. But in the real world, it changes with heat, it has a tolerance, it breaks. So we're going to look at resistors, capacitors, inductors, but we're going to do it by torturing them a little bit.
Torturing components for science. I'm in. Let's go back to that pencil experiment I started with. It does sound a bit simple for a college course, doesn't it?
It seems simple, but it anchors the physics. Students take a pencil, draw a 10-centimeter line, and then they don't just admire it, they treat it like a lab specimen.
So they're marking it off, every centimeter.
Exactly. They mark off 1 centimeter intervals and measure the resistance at every single step.
So you get one value at 1 centimeter, a different value at 2.
And you get a linear increase. You plot resistance versus distance, and it forms a beautiful straight line. It proves that resistance is a function of length. You've just built a variable resistor from scratch.
Okay, so they make their own resistors, but then Dr. Godre also makes them check the ones they buy. And looking at the notes here, this part sounds, a little tedious. Measuring 1,000 resistors.
It is tedious, but that is the entire point. This is the statistical reality check.
But why 1,000? I mean, if I buy a 100-ohm resistor with 5% tolerance, isn't it just 100 ohms?
Almost never. It might be 98, it could be 104. If you measure just one, you learn nothing about the manufacturing process. But if you measure 1,000 of them and plot the values using Python...
You're not looking for a single number anymore.
No, you're looking for a shape.
The Gaussian curve.
The bell curve. You see that the values cluster around the center, but there are tails on either side. It teaches you that you can't design a circuit assuming a part is perfect. You have to design for the distribution, for the spread.
That's a good life lesson, actually.
Yeah.
Nothing is ever exactly as advertised. Now, speaking of imperfect, let's talk about the stress tests. I see a note here about filing a resistor, with a metal file.
Yep. Destructive testing. You take a standard resistor and you literally start filing away the material.
You're making it thinner.
You're reducing its cross-sectional area. And just like with the pencil, resistance depends on length and area. If the pipe gets narrower, it's harder for electrons to flow.
So the resistance just shoots up.
It shoots up, but you can't exactly put the material back on.
Right, it's a one-way trip.
It is. It's a very visceral way to understand that these little beige blobs are physical objects.
Okay, let's move to capacitors. Now, usually I think of a capacitor as a bucket. You pour charge in, you pour charge out. But apparently these buckets have holes.
All real buckets have holes. This is the leakage experiment. Ideally, you charge a capacitor to 5 volts. It stays at 5 volts forever.
But in reality?
In reality, internal resistance slowly bleeds that charge away.
So how do you measure that? Can't you just hook up your multimeter and, watch the voltage drop?
You could, but you would be lying to yourself.
Why?
Because the multimeter has its own internal resistance. It draws current to make the measurement. So if you leave it connected, you're the one draining the capacitor, not the leakage.
Oh, right. The observer effect.
It's a classic case. The tool changes the outcome.
So how does Dr. Godre get around that?
The method is really clever. You charge the capacitor to 5 volts, then you disconnect everything. No meter, nothing. You wait, say, 30 seconds.
And then you measure it.
You do a quick snatch measurement, check the voltage, write it down, and then, this is the key, you immediately recharge it back to 5 volts before you wait for the next interval.
I see. So by topping it off every time, you're resetting the start line. You're making sure the drop you see in the next minute is only from the capacitor's internal leak.
Exactly. Not from the energy you stole during the last measurement. Then you can fit those points to a discharge curve and calculate the actual internal resistance. It turns a feeling into a hard number.
I like that. It's detective work. Now, on the other end of the spectrum, there's the fuse test. This sounds a bit more explosive.
This is about respecting energy density. Students take a massive capacitor, we're talking thousands of microfarads, charge it up, and then short it through a tiny hair-thin wire.
And I'm guessing the wire doesn't make it.
If there's enough energy, the wire vaporizes instantly. It acts like a fuse. It's a loud, bright reminder that even at low voltages, the energy stored in a capacitor can be dangerous.
Visualizing that energy flow seems to be a theme. I was looking at the diagram for circuit B. It's a manual setup with 2 switches.
Right, it helps you see the handoff. You press one switch, current flows from the battery into the capacitor, an LED lights up, you see it charging, then you let go.
And the capacitor's just sitting there, charged.
It's a tiny temporary battery. Then you hit the other switch, and a second LED lights up, powered entirely by the capacitor, and it slowly fades as the energy drains.
Simple, but really effective.
All
Okay,
right.
I want to get into what you call the black magic section. Inductors.
Inductors are fascinating. It's all about magnetic fields, which always feels a bit like wizardry.
The experiment that really caught my eye is the 10.1 probe mystery. We all use oscilloscope probes, but I admit I rarely think about what's actually happening inside that plastic handle.
And that can get you into a lot of trouble. In this experiment, Dr. Gaudry basically simulates what a probe does. He has students start with a square wave, a signal that goes straight up, flat across, straight down.
A perfect boxy shape. Got it.
He splits that signal into 2 paths. One goes through a low-pass filter, and one goes through a high-pass filter.
So a low-pass filter lets the slow stuff through.
Right. It integrates the signal. It hates sharp corners. So instead of a square jump, you get a slow, lazy slope up and down. It looks like a shark fin.
Okay. And the high-pass filter.
It only cares about fast changes, so it sees the vertical edge and lets that through as a sharp spike, but it blocks the flat part. So you just get these weird needles.
So you've got a shark fin on one channel and needles on the other. Neither of them looks anything like the original square wave.
And here's the magic. You connect the outputs of those 2 filters together, you sum them.
And what happens?
The shark fin fills in the gaps between the needles. The needles sharpen the edges of the fin, and poof, your perfect square wave reappears on the screen.
That is wild.
That is exactly what happens inside a 10.2.1 probe. The probe has capacitance, the scope has capacitance. They act like these filters. When you turn that little compensation screw on the probe,
You're tuning the filters.
you are tuning them so they cancel each other out perfectly. If you don't, your scope is lying to you. You're physically balancing the math.
Speaking of physical things, let's talk about dropping stuff.
Yeah.
Lenz's law.
A classic. You wind a huge coil of wire around a clear tube. You hook up 2 LEDs to the coil, but you wire them anti-parallel.
So one point's one way, one point's the other.
Correct. So current can flow left or it can flow right. Now you take a magnet, mark the north and south poles, and you drop it down the tube.
Gravity takes over.
As the magnet enters the coil, the magnetic field grows. This induces a current in one direction. The red LED flashes.
Okay.
But as the magnet falls out the bottom, the field collapses. The change is in the opposite direction.
So the current flips.
It flips. The red LED goes dark, and the green LED flashes. So you see red-green.
And if I slip the magnet over and drop it south pole first?
You get green-red. It's visual proof that the direction of the induced current depends on how the magnetic field is changing.
I love that. Now, one more inductor behavior that feels counterintuitive, the inductive kick. The notes mention circuit A, where you have a 3-volt battery and 3 LEDs in series.
So let's do the math. An LED needs about 2 volts to turn on, 3 in series need
6 volts. And we only have a 3-volt battery. So physically, those LEDs should never, ever turn on.
They should be stone cold dead.
Mm.
But in the circuit, they're connected in parallel with an inductor. You close a switch, current flows through the inductor. The LEDs are dark. But then you open the switch,
You cut the power.
and the LEDs flash brightly.
Oh, you just removed the battery.
Think of current in an inductor, like water in a heavy pipe. If you have water rushing through and you suddenly slam a valve shut, what happens?
Get a bang in the pipes. Water hammer.
Exactly. The momentum of the water crashes against the valve. In an inductor, the momentum is the magnetic field. When you cut the circuit, that field collapses instantly, and it forces the current to keep moving.
And that force creates a voltage spike.
A massive one. It easily jumps from 3 volts to 10 or 20 volts for a microsecond. That's the kick. It's how spark plugs work.
The water hammer of electricity. Okay, we've tortured resistors, abused inductors. Let's look at semiconductors, specifically the Sherlock Holmes identification method.
This is a great skill. You find a transistor in a drawer, the label is rubbed off. Is it NPN, PNP? Which leg is the emitter?
I know finding the base is easy with a multimeter's diode mode, but emitter and collector usually look identical.
Structurally, they're very similar, but not identical. The emitter is much more heavily doped, chemically treated than the collector. Dr. Gaudre teaches students to use the multimeter to measure the forward voltage drop, the base emitter junction versus the base collector junction.
And they're different numbers.
Very slightly. The base emitter voltage is usually a few millivolts higher because of that doping.
Yep.
If you trust your meter, you can distinguish the 2 pins just by looking at that tiny difference.
That is some deep forensic electronics. Let's bridge the gap to the systems section. We talk about components, but also how they talk to each other. The outline mentions op-amps.
Operational amplifiers. The textbook says an op-amp has infinite input impedance and 0 current flows into the inputs.
But I'm guessing Dr. Gaudre says measure it.
He does. And you find out there is a tiny input bias current. It's nanoamps maybe, but it's there. And if you have a huge resistor connected to it, that tiny current can create a voltage error that messes up your whole system.
Which leads us perfectly to the most famous experiment in the book, the lemon battery.
Yes. Everyone has done this. Stick a zinc nail and a copper coin into a lemon.
Right, so why is a university engineering class doing it?
Because in grade school, you just celebrated that it worked. Here, they analyze why it works so poorly. They characterize the lemon as a voltage source.
They measure its impedance.
Exactly. They fabricate the battery, measure the voltage, and then they put a load on it and watch the voltage just collapse.
Because the lemon has a huge internal resistance.
Massive. It just cannot deliver current. And they compare this to AA batteries, lithium cells. It's a fundamental lesson in source impedance.
And this actually matters for modern stuff, like Arduinos.
It matters immensely. This is the bridge to the digital section. Students use Arduinos to read sensors. But here's the catch. The Arduino's analog input expects a signal with low impedance.
So if I hook up a sensor that behaves like a lemon, high resistance, the Arduino gives me garbage data.
Exactly. The Arduino has a tiny capacitor inside that needs to charge up to take a reading. If your sensor is too weak to charge that capacitor quickly enough, you get a wrong number.
So the lemon experiment isn't about fruit. It's about understanding why your expensive digital sensor might be failing.
Precisely. It's about matching the source to the load.
Wow. Okay, so this all culminates in the final fabrication project, making a real PCB.
Right. They learn KiCad, which is design software. But the hardest lesson there is the difference between a schematic and a footprint.
Oh, I've messed this up myself.
Yeah.
In the schematic, a resistor is just a zigzag line. It has no size.
But on the board, it has to be a specific physical object. Is it 5 millimeters long? A surface mount chip. If you pick the wrong footprint, your beautiful board arrives and the parts physically don't fit.
And I saw they use vernier calipers for this.
Yes, the show and tell boards. Students physically measure the components. They hold the object, measure the pin spacing, and then select the footprint. It forces that connection between the digital library and physical reality.
And then they actually etch the board themselves.
Toner transfer method. Ironing the design onto copper, soaking it in acid. It's messy, it's chemical, and at the end, you have a board you made with your own hands.
From drawing a resistor with a pencil on day one to etching a circuit board at the end, it's a complete loop.
It is, and it completely transforms the way you look at electronics.
So if we step back and look at this whole workshop, what's the big takeaway for you?
I think the lesson is that the map is not the territory. The schematic is a map. It's clean. It's ideal. But the territory, the real circuit, is messy. It has resistance where you don't want it, capacitance where you don't expect it.
And physics that will bite you if you ignore it. You have to characterize the reality, not just trust the simulation.
Exactly. Dr. Gaudre is teaching them to be skeptics. Measure it, model it, don't just assume.
I love that. Skepticism as an engineering tool. Well, here's a final thought to leave you with. We started this talking about pencils as resistors and lemons as batteries. It makes you wonder, where does the line between nature and machine actually end? We aren't really building artificial things, are we? We're just reorganizing the dirt and rocks until they do math for us.
That is a thought worth pondering. Reorganized rocks doing math.
Thanks for listening to this deep dive into the electronic design workshop. Go take something apart today. Safely, of course. We'll see you next time.
Goodbye, everyone.